All right, so the first thing we start talking about is going to be the soil profile. And so this is a very wide range here. There are a lot of subcategories that would normally be in this. If you take a soils class, it's going to be a lot more than O, A, B, and C. But we are going to focus on A, B, and C today of the soil profile. And O, I have left O out, even though it's in this photo, but O is really going to be mostly your leaf litter type situation as it starts to break down. And so it's not quite topsoil yet. It's going to be a lot of that organic matter that's starting to break down. And then we get into A, which we consider your topsoil. B, we call your subsoil. And then C is your parent material. So with your A horizon, this is usually the coarsest texture. It's the most fertile. It is usually the darkest in color. So the darker this one is, the better. That's what we like to see in there. It is, of course, highest in organic matter. Like I said, O is really, as that starts to break down. So it makes sense that A is going to be your darkest in organic matter. And this is where plants are obtaining most of their nutrients as well as their water. And so because we have high organic matter, it means, and we're going to talk about this a little bit later, but high organic matter means high water and nutrient holding capacity. So it makes sense that most of our root system is going to be in this topsoil. And this is true of things like trees. A lot of people don't realize, I know when we think of trees, we're always taught, oh, their roots go down so deep and they search for water really deep. And while that's true, a lot of our trees have nice big tap roots. They're going to have some good anchor roots down in that soil. Actually, majority of that root system is going to be in that top 10 to probably about 24 inches of soil. So that's why it's really important. And we're going to talk about the compaction and things like that. But while it's really important that we improve that topsoil layer. Then we get into the B horizon. So this is a little bit finer in texture. If you've ever, planted a tree or something larger, you've probably gotten into subsoil before. Or if you are dealing with soil that has been disturbed or topsoil has been removed. I know with a lot of homes, new homes especially, they've removed a lot of that topsoil. And so what you're left with is usually subsoil at the top. But this is finer. It's lower in organic matter. Therefore, it is lower in fertility, and it is either red, brown, or yellow in color, and that comes into play based on the parent material. It is a firmer soil texture, and it's going to be your reservoir for storage as well as water for that surface soil. So as you can see, I love this photo because it shows how majority of the root system is in that top layer, but you are going to get some roots that are going to dive into that subsoil, especially during times of drought. Or your longer lived perennials are really going to dig down in there. This also regulates your soil temperature and provides soil oxygen. And so as we know, your roots require oxygen as well as water and nutrients, but your roots are going to breathe and need that gas exchange just like we do. And so that's important. And that pore space down in horizon B is really vital. And then we get into our C horizon, the parent material. So it's usually a soil rock mixture. It's decomposing rock. It's very low in fertility typically, and it's that real light shade of color. Whatever B is, it's the lighter shades. We talked, it's red or brown or yellow. It's just going to be a lighter shade in C. And so that's what creates, B and a lot of those nutrients and pH. Parent materials, a lot of control on pH of our native soils. So here in the bluegrass area where I am, we have, of course, and I know a lot of the Kentucky area, but we have limestone parent material, right? And so we have heavy shale and things like that. So that's our parent material, which affects our pH and available calcium in our soils. And so here we have a photo which kind of shows those. And so that top layer, just really, it's a very small layer of O where you can see that decomposing grass. So right underneath there where you're going to have that decomposing root system, you're going to have a lot of microbes and macrofauna like your beetles, your earthworms, different things like that are going to be in that O layer. So it's real thin. And then we get into that A, which is going to be this darker area in here you can see, and that's a really nice color that we like to see in our O. or in our A, and then we move down into sort of that red color, much lighter. That's your B horizon. So it's, got that bigger pore space down in there. It's starting to get more rockier, as you can see. And then all the way at the bottom is going to be, you're starting to get into your C. So it probably gets even lighter as you keep going down. And you can see how it texturally is going to change as it moves throughout here. Okay, so now we're going to talk about properties of soil that are important to plant growth. And we're going to just kind of barely touch on all of these. Like I said, this is a real basic course. I'm happy to entertain any questions that are a little bit more specific based on these. But properties of soil, especially for plant growth, is going to be all three of these things combined. You've got your physical, your structure. It's exactly what it sounds like. Is it compacted? How poor is it? How does water move throughout? You've got your chemical, which is your pH. Most of us know what your pH is, and hopefully you know what your pH is, at home, but we all know what it is. But your soluble salts, how much nutrients it can hold onto, which again plays into your physical parts there. That's why we see these overlapping. And then of course your biological, which is your macrofauna, so those larger, animals of, worms and insects and spiders and things like that, getting into your microfauna, your nematodes, your microbes, things like that, your microorganisms. Roots, of course, are alive and they're feeding down there in the soil. They're building relationships with fungi and things like that. And then your organic material again. So all of these overlap to create a good soil. And so we're going to hit on a couple of those more, I don't want to say important ones, but just sort of ones that you're going to come in contact more when you're dealing and trying to maybe improve your soil. So texture is the biggest, and I don't know if I want to necessarily say the easiest. It is a pretty easy thing to understand because we all know sand, silt, and clay, right? Those are the three components of soil that make up the texture and the structure of soil. So sand, of course, is a loose grain. We've probably all been to the beach or at least have seen some playground sand before. And so we all know what sand is. It's going to be large. A single grain of sand is, visible to the naked eye. It's easy to differentiate from something else. Your silt is going to be just silt by itself feels just like flour. And so it's got that silky, smooth texture to it. And then of course, clay. And if you've ever done any digging anywhere in the state of Kentucky, you know what clay is. And so clay is going to be that slick, very sticky when it's wet, kind of Play-Doh-y type consistency. And so I like this picture just to show the difference. One thing to note here is that clay under a microscope is flat, right? Where you can see here your silt and your sand are going to be round in shape, where slick, and that's what creates that kind of sticky wet. Sticky when it's wet, it's very slick because these are plates rather than some circular granulars out there. And then I really love this description to talk about the difference in size between these, because it's very hard to, at least for me, to comprehend the size of clay in comparison to sand, because sand is still very tiny, even though we can see it. And so I really love these descriptions. So if sand is the size of a basketball, then silt is going to be a golf ball in comparison. And then clay is going to be a lifesaver. And I like lifesaver because it is, sort of that flat as well. And so think about the difference between a basketball and a lifesaver. And then you think about how tiny a grain of sand is, and that's you talk about how small clay is going to be. And so that's why when we have heavy clay soils, we have our porosity changes. And we're going to get into that here in just a second. Okay, so benefits, a lot of people say, well, clay is bad, or, sand is good, vice versa, but really we kind of want all of those things. And here is why. And this always makes me think of Goldilocks and the Three Bears when we talk about these, except none of these are just right perfect, even though silt is pretty close. So with your sandy soils, we get fast infiltrations. We get water moving into that soil. We get nutrients moving into that soil very quickly, which is a good thing. But what that also means is that it leaches really quick. And so again, that's kind of common sense when we think about it. You get waves coming up on a beach. they filter back through the sand and goes back out. It doesn't stay with puddling happening. It has, of course, low water holding capacity. There's just not anything to grab on to those water molecules, just runs right through. But then it's easily tilled. And so, of course, you can imagine, if you've ever run a rototiller before, you can imagine rototilling sand, right? It's kind of pointless. And then it has a rapid spring warm up. Because we have so much pore space in there, we can get a lot more air into those pores, and therefore that air can warm up and warm that soil up very quickly. When you move down into silt, remember that's your golf ball size. It's the medium, right? It's medium of kind of everything. It infiltrates pretty well, not as good as sand, but it also leaches, but not as much as sand. And so it's right in the middle of everything. It is still very easily tilled. Again, if this is flour in consistency, you can imagine tilling through flour would be very simple. It medium spring warm up. This is what causes surface crusting. So I know a lot of us think that when you see during really dry periods of time, you get the cracking of the soil, but you also get that crust that forms where at the edge of the cracks, it kind of flips up a little bit. I don't know if any of you have seen that before. Where I grew up, we had crusting all the time, but that is actually silt and not clay that's doing that crusting there on the sides. And then of course, clay is the opposite end of the spectrum. We get slow infiltration, but therefore we get slow leaching. So we're not losing all of our nutrients and water into that water table. It has high water holding capacity. We know this because it's very hard to till, especially in the springtime, and probably for most of you in this state, because we have heavy clay. We have to wait a long time for it to dry up. And if we know anything about spring in Kentucky, there are very few times when it does dry up. And because it has much smaller pore space, it is very slow to warm up in the springtime. So, right, it's the very opposite of sand. And so all of these, none of these are bad, none of these are good, they just are. And so what we then talk about is your ideal soil is going to be what we consider a loam. I'm sure most of you have heard about this before. People will ask you, what kind of soil do you have? Your goal would be a loam, right? And it is a desirable soil. You can see it right there in that brown gold color in the middle. And it has moderate amounts of all three of our textures here. It has some clay, some silt, some sand. It has, a little bit less clay than it does silt and sand, but what that does is it makes sure that, yes, we can get good penetration of things, but we also have clay to hold on to those nutrients and that water while still being, relatively easy to till and all of those good things we love about silt and sand. And so this is a very simple textural class, a little pyramid that I have here. There are more than 20 different soil classes out there. And so this is just an example. So I know here in the bluegrass on my farm, we have a clay loam. And so not all bad, it's just maybe a little bit more clay than, what would be considered desirable, but it is still a loam. We still do have those pieces of silt and sand, which make it desirable. And a lot of Kentucky has some version of loam in them, depending on where you're at. So hopefully or you will know soon after this class, what kind of loam soil you have. So one way to find out what kind of loam soil that you have, and there's a link here that will help you with the ribbon test. We try and do this in our Master Gardener class, but what you do is you're going to take some of your soil, you're going to wet it down and do what you call the ribbon test. And so you can see he's creating this ribbon, or she, actually don't know if it's he or she. They are creating a ribbon with this long ribbon between their thumb and their fingers. So they've got a ball of their soil in their hand. And they are just pushing it through and seeing how long of a ribbon they can create. The longer the ribbon, the more clay is in it, because remember, clay is sticky when it's wet. So it holds on to each other. So the longer it is, the more clay you have. And this is a really simple and free way for you to get pretty close in figuring out what kind of loam or not loam that you may have at home. And so without doing anything too crazy, you can figure that out. And it is pretty accurate. I know even people who are pretty inexperienced can get really close, if not dead on, what type of soil that they have. And there's contests on people who are trying to figure out one of those 20 soil classes based on those ribbons. So this is definitely something doable for most of you. And then I keep bringing up pore space. I keep saying those things. So let's talk a little bit more about that. So pore space, exactly what it sounds like. It is a space between your soil particles, whether that's a sand, silt, or clay particle. It's the space in between them. So this pore space is going to be filled with either air or water. This is also where your roots are going to move. And so they're sometimes are breaking through particles, but most of the time they're taking the path of least resistance, which is going to be around those tiny particles and through those pores. So, you know, this is going to be really important when you think about things like compaction. So when you compact a soil, you are minimizing that pore space. So therefore, you're minimizing the amount of water, you're minimizing the amount of air, and also the ability of roots to move through that space. And so that's why compaction can be such a big deal. There's just not enough area to have water and air down in there. A soil solution, so that's something to think about, is the liquid that fills the pores in between your soil particles. And this is where most of your ions are available for plant growth. And so most of the time with most your fertilizers, again, this is what we get into a little bit more in depth and maybe is a little bit more, but we talk about cations and anions, and those are your things, your different fertilizers, right? And they stay in solution or will adhere to the edges of those textural elements, so sand, silt, and clay. And so as your root is moving down through there, it can collect those, so to speak. And again, that's a really simple way to put it. My soil microbiology teacher would be very disappointed in me describing it that way, but it's simple. That's how it works. The root moves down through there, it collects those fertilizers. And so again, if it doesn't have that pore space, then those roots can't pick up those ions and to help with plant growth. Okay, and then getting into soil chemistry. And so chemistry is not my strongest subject, I will be honest with you, but we're going to hit the basics and sort of the simple things that will maybe help you understand your soil test a little bit better. And so one thing you see in your soil test is your CEC, which stands for cation exchange capacity. And this is the soil's number on how many exchangeable cations it can hold, okay? And so a clay soil, remember, it can hold on to a lot of things, and so it has a higher CEC than some of your other soils. So as well as organic matter. And so your cations are going to be, again, those fertilizers, those good things that we want our plants to have. So the higher organic matter you have, or the higher clay you have, which is one of the reasons clay is not all bad, the more nutrients that soil can hold on to. And that's why we apply organic matter to our soils, because we want to be able to hold on to all that good stuff that's going into those. So a low CEC usually means low organic matter. So you have low clay, you may have eroded soils. So you're maybe down more to that that parent material or that subsoil material that we talked about earlier, that BC horizon. Or you have very sandy soils. And so people, I know in the Pacific Northwest, have much more sandy soils, much more silty soils, and they have to apply some sort of fertilizer, whether that's organic or conventional, a lot more often than we would, because they don't have the clay, they don't have that high CEC. So the higher your CEC, the more cations your soil can retain, which means it's harder to change your pH. So if you are, for example, trying to grow blueberries, that's the easiest thing to think about when you're trying to change pH. Most of us in the state are going to have a pH around neutral, and we're going to talk about that. So if you're wanting to lower that pH or raise it for some reason, it's going to be a lot harder to do when you have a high CEC, because that organic matter, that clay, is already hanging on to so much that it's hard to get it to hang on to something different that you want it to. And so that can get a little bit complicated, but just know if you're trying to grow blueberries, you're trying to lower your pH, but you have a high CEC, it's going to take a lot longer to change that pH over time. And then we've talked about this. So clay content, organic matter, increased CEC, sandy soils have have a low CEC. I'm going to just, part of soil understanding soil science is just repeating the same thing, and finally it will click depending on how I'm relating it to things. So why is CEC important? So when you get that back, and some of you will have CECs that can't be calculated because your pH is too high. And what that indicates is you have high nutrient holding capacity. That's what we want. These soils, retain the nutrients between fertilizing events. So if some people might have to fertilize twice as much as you do if they have sandier soil. This also helps with nutrient leaching, so we're not losing that fertilizer into our water table. And we all know how bad that is. That's a good thing. And then it provides a buffer from abrupt changes in soil salts and pH. So if you accidentally dumped a bunch of sulfur in an area, and of course it's very hard to get back up out of your soil, you don't have to be too stressed if you have a high CEC, because it's going to buffer that out and you won't really get a dramatic change. Again, good in some situations, bad in other situations. And so then if we move into soil pH, kind of talking about that, it's the measurement of hydrogen or acid forming ion activity in the soil, which is, again, chemistry, and it's not my favorite topic here, but I'm not sure why I'm losing part of my text. I apologize for that. But this essentially measures acidity or alkalinity. And so there's 14 pH units. They're centered around neutral. Water is considered neutral at 7, or hopefully is neutral, just kind of depends, I guess, where you get your water from, but that's what we base it off of. You'll hear people call your soil sweet or sour, and that was something that my Yankee parents did not know. And so I remember when I heard an old farmer here in the Danville area call his soil real sweet, I was very, very confused. Okay, but what that means is your soil is sour if it is below 7 on the pH scale, and it is sweet if it is above in an alkaline, so it's above 7 in your soil. And I think that comes down to actually tasting your soil. Somebody can feel free to correct me on that, but that is always what I have heard. And so when we want blueberries, we want an acidic soil, so it would be more sour. When we want to grow tomatoes, usually they're going to be more on the acidic side as well. But something like a geranium likes a more alkaline soil, like something closer to 8 ideally. So it just depends on your plant and what they want. And so the reason why pH is so important is because it affects your nutrient availability. And so I really love this chart because it shows, and again, this goes back to chemistry, your positives and your negatives, and we're not going to go into that. But what this shows is what is available to the plant based on the pH. And so again, if we go back to blueberries like something between, it's usually around 4.2 to 5.2, somewhere in that range. They're typically happy. So if we look on this chart and we look over around the 5, what we see that's heavily available is iron and manganese, boron, copper. Those are all things that blueberries need, which is why we have to put them down in that more acidic pH range. Other things can be tied up or at toxic levels if the pH is wrong. And so, acid soils, your calciums, things like that, your alkaline soils, iron, others are not available if it's too alkaline. And so most plants are going to be somewhere around neutral, unless, again, there's extremes to each cases, but they're going to be somewhere around neutral. But plants, there's some that, like viburnum is a really great example. There's lots of different native viburnums to Kentucky. And what that means is that they're pretty variable. They can have a wide range of soils that they will grow in. Of course, they have one that they'll thrive better in, but they'll grow in, kind of both ends of the spectrum. So now we're going to move into talking about NP and K. I'm going to hit very briefly on fertilizers here because I think that's important when you're going out and you're not sure what fertilizer to get, or you're gotten your soil test back and, Amy or Kelly or whoever has been doing your soil samples is going to tell you what you need, but it's helpful to kind of understand where that's growing. So things to keep in mind, and these are very, very general ways of putting this. I'm well aware all of these things, NP and K, contribute to lots of different things going on in the plant, but this is a very general way to think about it. So nitrogen is for your leafy top growth. So if you have a plant that is not blooming, and it should be blooming, so that could be a tomato, that could be a zinnia, that could be a house plant. If it's not blooming, it could be that it's getting too much nitrogen. It's pushing green growth rather than your potassium and your phosphorus. Phosphorus is root and fruit production. And so that goes into that fruit production goes into bloom. So maybe it's not getting enough phosphorus. And then potassium is cold hardiness. It helps in disease resistance and water uptake and just kind of general plant durability when you think about it. And so we usually think of this as N is for leaf, P is for bloom, and K is for root. And that's, again, very, very broad way of putting it, but it can be really helpful when deciding what your plant might need. So when you go buy a fertilizer, whether it's organic or conventional, all right, it's going to have these three numbers on it. It's going to have N, P, and K on it. And you can see them here. I'm sure all of you have seen them. Does not matter what kind you're buying, it's going to have N, P, and K. Even if you're buying sulfur a lot of time, which has none of these things in it, it will have a 000 to tell you it has no nitrogen, phosphorus, or potassium. These numbers are percentages by weight. And so what that means, if you look at that top Scott's one, that 2833, that means it is 28% nitrogen, 3% phosphorus, 3% potassium. Okay, it's always in that order, NPK. So 16% nitrogen, 8% phosphorus, 8% potassium. Always in that order, and that's something that you want to look for depending on what you're buying. All right, I highly recommend that. Some tips for nutrient management in your soil. So remember, heavy N fertilization before flower on tomatoes, as an example, encourages all vine and no fruit, because remember, N is your leaf maker. Slow release fertilizers or manures, they can cause this problem sometimes, and they push fruit and vegetable production to late in the season. And so it's not always bad. It's not saying you're not going to get any fruit at all, but it's going to push a lot of upward green growth. And so if you've been wondering why your tomatoes or squash or anything like that seems to be a huge plant, but you get very little bloom on it, this could be why. You want to keep soil pH level somewhere between 6 and 7. Again, this is really dependent on what you're growing, but majority of our garden plants are going to appreciate a pH between 6 and 7. Use organic matter. So soil microbes in that organic matter, they decompose the nutrient and they release it in a plant usable form. So this is the biggest difference between conventional and organic fertilizers. So organic fertilizers are not yet in a plant usable form. And so they take time to become usable because microbes have to decompose them. Versus a conventional fertilizer, something like Miracle Grow that's water soluble, is immediately plant usable. So there's no microbes that are needed to make that NPK available to that plant. So I'm not saying one's better or worse than the other. I'm just saying that's why when we think about organic, we often consider those more of a slow release because it takes time to break those down. When you do apply fertilizer, you usually want to band this in at the root zone. And so I don't like putting it in the hole that I plant in because that can burn your roots. Again, whether it's conventional or organic, you can get root burn because fertilizer is a salt when it comes down to it. But you can band this in at the root zone right on the top. That prevents weeds from taking up fertilizer that you want for your squash. And then good watering practices maximize nutrients. So a good example of this is going to be blossom end rot on tomatoes, peppers. You even see this on squash. Blossom end rot is caused by a lack of calcium while that fruit is forming. So calcium moves in water. In most of our Kentucky soils, there's always an exception to the rule, but in most of our Kentucky soils, we have a limestone base, which means we have high calcium in our soils. So there should rarely be a reason you should ever have to apply calcium or magnesium for that matter. What it means is that you need more stable watering. You need more consistent watering because calcium can only move in water. And so usually that is the case when I have that, in my counties, and any other agent, feel free to chime in here. But When we do soil tests on people having problems, their calcium is always where it needs to be, so that they're not watering consistently enough. Okay, and that's it. That's the end. That's my spiel. So now is when we start taking questions, and hopefully I can answer them. I really enjoy soils, but I don't claim to be the expert. I just like it. And also, don't ever call it dirt. It is not dirt. It is soil. Dirt is what you sweep under your rug when your in-laws are coming over. Soil is what we grow plants in. Okay, so I'm just saying.